This is Steve. This is my 2N5109 preamplifier that I've just recently finished building to, I'm going to plan to deploy it out on my 9-circle high impedance receive array. I already have another device out there, but I thought I'd design my own here in a metal box. I mean, the idea may be, with this metal enclosure, I could either mount this at the shack against my low impedance ground plane entry panel, or mount it even outside at the array. The idea with the box, I mean, perhaps, I mean, any common mode noise on the outside of the coax, will just stay on the outside, and it'll maybe minimize any kind of noise ingress. But mostly, look, I've been having a lot of fun building my own circuit board, so I thought I'd, design my own rendition of Larry W7IUV's very famous 2N5109 amplifier. There's a lot of stuff online about this, but I'll try and dig up the reference which I have and include a link to it where Larry very clearly describes the specific component values for this amplifier. And I must tell you, and I will show in a moment here, I'm going to show some of the testings that I've done both with the AIM 4170 as well as the Nano VNA, and his component values, he nailed the values in terms of the impedance for sure, and the gain. I mean, the input and output impedance, this amp is built to be a 50 ohm system, and it is virtually exactly 50 ohms as he described it. So what I did, of course, the 9-circle array is a 75 ohm system. So I've included a couple of just simple transformers in order to match the 50 ohms to the 75 ohm system. And the other thing that's vital with a 9-circle array, in order not to upset the pattern, it's very important that the input to this amplifier, which is going to the 9-circle array, be as close as possible to 75 ohms. So I've included an attenuator in here at the feed point to try and mute any kind of impedance bumps that might show up on a mismatched coax. And I'll show the measurements I did that I think I've pretty much got it to be an exact 75 ohm output. The mount and the physical layout here is such that I was able to source, a 12-volt connector that's similar in profile to the F connectors, except not exactly. So you need to include a little nut here, but then it'll be a perfect little mount for a box. I mean, you could put it in a metal box, or you could put it in a plastic box as well if you wanted. It does include a low impedance ground plane across the entire board. So I mean, it's you probably don't have to put it in a metal box. I'll include a link to the KiCad design in case you wanted to upload this and build it yourself. I also include on the silk screen on the front, indications where if you didn't want to turn it into a 75 ohm system, you could just use a jumper and short out where the transformers go, and then you'll be a 50 ohm system. Of course, you'll still be left with 75 ohm F connectors, but I don't think that's a big deal. Anyway, hey, look, I'll just now just show you some of the results I got from testing this amplifier and some of the experiments I did with the attenuators to try and smooth out especially the input impedance. And I'll also show the gain curve using the Nano VNA. A little bit of background on the 2N5109 amplifier. This device was popularized by some great work done by Larry W7IUV over the great many years, actually. The circuit was originally published in the ARRL handbook, but Larry did a whole lot of work modifying the component values and testing to maximize the IMD performance, and was very kind to share his results online and his development over the years, for that matter. I personally have built at least 12 of these amps over the years, and they've worked extremely well both in the shack and out in the field with virtually no failures. A lot of different design approaches, a dead bug, point-to-point type of construction, as well as a home etched using a marker and ferric chloride, that type of thing. But I would suggest if you plan to build one of these amps, or purchase some of the online variants. For example, on eBay, there's a lot of boards you can buy and whatnot. I would strongly recommend that you read Larry's comprehensive documentation that describes his design and the importance of each selected component value on performance. For example, the description in the 014UN book version isn't quite correct. Now,
I was unable to access W7IUV's webpage directly. It seems to be inactive right now, but I did find this link to his revision 5 documentation. The link shown here, but I'll include that link at the end of the video. But in it, he describes, he talks about each and every component in the circuit and what the importance of each value is. And I think, if you're going to make this, build one of these, make sure you read that first. What this design that I've done here, my design changes nothing. All it does is add input and output impedance matching transformers and an attenuator to stabilize the input impedance. And that's to make it suitable for my 75 ohm 9-circle receive array. I could have, well, I couldn't. I don't have the skill set to have somehow redesigned the component values to make it into a 75 ohm system. So this made a lot of sense for me to use, to take this approach. The truth is, this project is mostly a build-up test to ultimately integrate this amp into my homebrew 9-circle array combiner board. I'm going to build I'm designing my own circuit board, which will be used to be a combiner for my 9-circle, but I'm going to integrate on that same board this particular amplifier. So that's what the motivation was for doing this work myself. Here's the basic circuit design from that very document I was referring to. Again, in that document, he describes every one of these component values. By and large, I followed everything as he described, and in fact, his resistor R3. He does say that can be and sometimes needs to be adjusted to control and ultimately achieve the correct collector current, which is ultimately your supply current from your VCC. He described a 3.3K resistor being what was appropriate for his device. I found I needed a 2.2K for R3, and I believe that's a function of the device itself. The device I've described in my parts list at the end of the video here was from DigiKey, and that's the device I use, the 2N5109 transistor. So presumably you might be closer to the 2K. But if you build this thing, be prepared to measure the current drawn by the device and be prepared to adjust that, because you do want it to be in and around this 70 to 80 milliamps of current, which will get the device pretty hot. You do need a heat sink, but getting that current as high as he's described is important to maintain the IMD performance. As shown and as I explained already, this amplifier was designed to be a 50 ohm system. The input and output capacitors could be adjusted to refine that, but I just stayed with exactly the values he described. So this is the where I've basically included that same, or built up that same circuit in KiCad. So that I can put it into my PCB layout design. But you'll notice the only difference here is I've added the input transformer here, a 5-turn to 4-turn transformer to transform the 75 ohms to 50 ohm system. I mean, I could have used the tapped auto transformer type geometry. I just choose to use a symmetrical isolated transformer type approach. I mean, it works simple enough using a binocular core. And again, on the output, you'll see the same thing, a 4-turn to 5-turn 75 ohm to 50 ohm impedance transformer. The only other difference you'll see here is this attenuator pad, which I'll talk about in a moment. Here's a picture of the board from KiCad. It provides this ability to look at the board. But you'll notice on the silk screen what I've shown is, this is where the binocular core would be placed with the 5-turn to 4-turn impedance match. But I've just even shown on the silk screen. If you wanted to build this thing and stay with a 50 ohm system, well, you just jump across there and not include the transformer if you wanted. You can see the attenuator pad here. You could short that out if you didn't want to include the attenuator. There's the actual board. I ordered mine from OSH Park. You could order them from anywhere. I'll provide that KiCad file at the bottom of the video. So anyway, what I did was I used my Nano VNA that I bought, my new little toy. I don't know if you guys have seen these, but I got it. It comes out of China. The darn thing's like $60, and I mean it's a 2-channel vector network analyzer, and I can, not just measure, S11, but I can measure S21 through the device. So anyway, this is my setup that I use to do some testing. And this is the first one I did. So, man, like I said, Larry nailed this, the impedance, pretty close. So this is without the matching transformers. This is the input impedance with the output terminated in its characteristic 50 ohm termination. And you'll see that on, I've got 3 markers here. This is the 50 ohm line. Here, and you can see that I've got my frequency bands here. So this is 160 meters and 80 meters and 40 meters over here, and I've got my markers shown here. So 47.93 ohms, 48 ohms, 55 ohms. So pretty darn close to a 50 ohm input impedance, and the output impedance, 55 ohms, 50 ohms, and 52 ohms. So pretty darn close to his designed 50 ohm input and output impedance. So anyway, now let's include my 75 ohm matching transformers, both on the input and the output, and I did the same test. And again, in this case, of course, I've terminated the output of the amplifier with a 75 ohm resistor, and I'm measuring the input. And you can see here's my 75 ohm line with my 3 markers. What am I at? 76 ohms, 74.8 ohms, and 73 ohms. So pretty good match there, and that's pretty reliable for a 75 ohm system. So, okay, what happens if we terminate the output of this amplifier with a 120 ohm resistor? Okay, now this is a pretty severe mismatch, but nevertheless, you'll notice that here's my ideal, here's my my 75 ohm line up here. But now when we terminate the output with a 120 ohm resistor, well, gosh, we're way down here now to we've driven down the input impedance down to 55 ohms. Okay, a long way from our 75 ohms. So one trick here to help smooth out this impedance mismatch, of course, is to use an attenuator. You got your typical pi attenuators, or a T attenuator, or a bridged T attenuator. I chose to use a T attenuator mostly because of the geometry. And by the way, there's some great online resources. Just Google attenuators, and you'll find lots of information online where you can just plug in whatever impedance in and out you want, and whatever amount of attenuation, and it'll give you your values. The one thing about the bridge T, we don't really want to use a bridge T because that kind of eliminates some of the impedance matching, impedance buffering benefit of an attenuator. So I included the T attenuator, which you can see here. In this case, the design I have is about 4.2 dB, and it's a couple 12 ohm resistors and a 100 ohm shunt resistor to ground. And so when we do that, here's the results. So the green line is with the attenuator in the system, and you'll notice in this case, and again, I'm still a gross mismatch, 120 ohm termination instead of our 75 ohms. And you'll notice that here we're only 10% away from our 75 ohms at 67 ohms. Without the attenuator, we're a good 26% away. We're down around 55 ohms, as I just showed. So, the attenuator has really helped us out here. So now, what about a 50 ohm termination? So again, we're terminating the output of the amplifier in 50 ohms instead of its characteristic 75 ohms. And well, when we do that, you can see without the attenuator, that drives our input impedance way off the chart here. We're up at 100 ohms. That's 33% higher than what the 75 ohms it should be. But if we've got that 4 dB attenuator pad on the output, I mean that's really buffered things here. We're only 10% away. We're only 83 ohms from compared to the ideal 75 ohms. So I think the benefit of having this this attenuator on the output is, I think, worthwhile, because I mean, certainly it's highly unlikely I'm going to see any of these great mismatches that I've described here. 120 ohms or 50 ohms. I mean, my coax that goes to the rig from this amp is a 75 ohm coax. But I think with this attenuator, any kind of subtle changes or subtle variations should smooth anything out. And furthermore, here's my S21 gain through my VNA, and you can see that without the attenuator, this amp's giving me 20.4 dB gain, which is pretty much as Larry described it would. And of course, that pad the T pad that I put in is about 4 dB of attenuation. So there we are with the attenuator. I'm at 6.3 dB, and you know what? That's tons of gain. I mean, for the output of the 9 circle is such that that's more than enough gain. I could even put in a bigger attenuator if I wanted. So what about construction? Well, all the component values that on my silk screen are indicated, so you just plop them on where they're shown on there. And I've also I'll show I've included a drill out hole on the 12 volt connector so that you can mount it on the box. I'll show you that in a second. And you want to make sure that you're mounting both the 12 volt and the F connectors on the foil side. I'm going to show you just a second here. I'm going to show you the. So here in KiCad, I can show you the 3D view of things here. So you'll notice that on the 12 volt connector, there's a pin here, or a hole in the middle. Which the reason for that is you can just literally lay this board on the panel or the front panel of your mounting box, and if you use that hole in the jack as a drill guide, that'll provide the correct mounting location for both the power jack as well as, of course, these for the F connectors. But of course, make sure that you're mounting both the 12 volt jacks and the F connectors on the foil side, right? Because you want the components to be on the outside of the box mount. So I'll include the links for the KiCad files and the BOM at the bottom of the video. Again, as I already said, I really encourage you to read Larry's documentation before you build this. I mean, this is in no way comprehensive. It's I think incumbent upon any builder that wants to do this that they follow Larry's documentation. All I can provide here is a circuit board that follows his layout. Performance. I've had this particular device in service for 3 months this winter. I'd have to say really no greatly noticeable difference compared to the Hi-Z amp, which I originally had in service. Perhaps the impedance buffering, as I just explained, of the output attenuator might help the array performance, if there happens to be any feed line mismatches. There's a chance there might be slightly less noise compared to the Hi-Z. But I'd really have to do an A/B to compare. When I first installed the new amplifier, which is in the metal box, I was listening on one of my SDR radios, and I could see the noise, and it appeared to be slightly less. But gosh, that's far from quantitative. And by the way, here's the Hi-Z preamp, which is sold by DX Engineering that I did have in service. Great amp, worked perfectly. I had no problems with it. It's also a 2N5109 or a 2N3866 device designed for a 75 ohm input output. So here's what it looks like inside. So you can see this is the 2N3866 device, and it's essentially a similar design to Larry's, but his design is specifically for 75 ohms. And by the way, I did do a VNA sweep on it, and it's very close to 75 ohms input and output. No impedance buffering though, so if you have some mismatches, you got to watch that, because if you have a mismatch on the output of this amp, it's going to affect the input impedance. If you're matching a 9 circle array, that's not optimal. There's a number of other devices out there. On eBay, to buy boards. You could buy, kits as well as just boards alone. But again, confirm whatever component values you're installing and compare them to Larry's documentation. There's this device here on remoteqth.com. This one's kind of cool. It's got little SMA connectors, which of course makes more sense with a 50 ohm system. It includes some relay protection. And it's you can actually adjust the bias, rather than having to fiddle with that one resistor. It's actually got a variable resistor to adjust it, and it's actually got it's designed an ability to vary the attenuation and vary the gain. So other things that you could look at. Lots of other options out there. And so, as I had mentioned, the real purpose for me doing this is just a teaser because I'm not finished this project yet, but this is actually the PCB layout for my 9-circle combiner board. This is the same YCC Contest Club 9-circle receiver array designed by John W1 Fox Victor. And I decided to just fiddle around and make my own combiner box here. And you'll notice that the main combiner box components are here, along with with the switching relays. But in this corner here, I've included that very amplifier. I mean, these arrays do require amplification, so I thought, well, why not integrate it all on one board? And the one difference, of course, I'm also going to include is changing the output impedance from the combiner board to match 50 ohms, and then I can eliminate the need for this other matching transformer. And we can look at this in 3D and have a look at, this is kind of where I'm headed with this. And I may put up another video and show this. My intention is to mount this combiner box in an aluminum box as well, instead of the plastic box which came with the original YCC Contest Club design. 73, Steve, E6WZ.